in effect a massless particle.
Yeah, the time in black hole so slower.
Yeah, mass is infinitely.
Oh,
This was a story. A student gave this to me because I think this is a direct quote. I think she said it freaked me out.
Yeah,
so,
I was going to say it looks like a depressing children's story.
Yeah, it's written by Brian Greene, who's a very notable physicist. I think he's a string theorist more specifically, which some could claim makes him a mathematician. But so it's a cardboard book, so therefore you get the impression that it's a kid's book. And the student got it because she thought, oh, Brian Greene, children's book, that would be interesting.
Existential crisis.
All right, so they are. There we go. All right. So about some guy named Icarus who flew too close to the black hole. All right, so on the board to run about, Icarus was in high gear. His hands raced across the console, adjusting here, fiddling there. He just measured the black hole's mass, so he knew precisely how close he could safely venture. Because there's an event horizon, you don't want to go into it. And so on he went, perfectly executing a glancing trajectory in which he momentarily swooped to a hair's breadth above the point of no return. The runabout performed exactly as he had calculated, easily pulling away from, oh, there's the picture, because he's closer. That's a previous picture.
Oh.
And then closer.
And everything looked like blue when in the black hole.
Say that again?
Yeah, the light is everything it turned to blue when we pass out the horizon.
Oh, the light that comes off of black, not out of the black hole, but off the black hole. Is that what you're talking about?
Yes. Never mind.
Okay. All right. So just from the black hole's edge, 2, 3, 5 times he completed the same maneuver, even doing a full circle around the black hole's horizon on the last whirlwind ride, hovering along the very edge of the gravitational abyss. Icarus's heart was pounding as he pulled away from the black hole for the final time, headed back towards the Proxima. That would surely be remembered, he said to himself as he flipped on the radio. Dad, what do you think now, he asked, trying his best not to sound too self-congratulatory. I'm the first person to journey to the edge of a black hole. There was no response. He hailed the Proxima again, that's the mothership. No answer. Could the black hole have disrupted the radio, he wondered? But he couldn't think of any reason why that would happen. He approached the location where he left the Proxima. Icarus couldn't believe what he was seeing. Hundreds of enormous luminous starships of design he had never seen were rushing along and it appeared to be an interstellar highway. What in the world is going on? Icarus asked himself, slowly and quietly. A patrol ship, larger and even more imposing than the others, approached the runabout and signaled him to dock. So, in essence, everyone he knew was dead.
Because he went so fast.
Because he got so close. Because not only does speed affect it, that's the special relativity, but black holes works time and space. And so black holes will also disrupt time. The math behind that, I will definitely not go into because I don't even understand that myself. General relativity course I took in college kicked my ass. So. Alas, oh well.
That would.
Yep.
I can see why that would freak could freak people out. I mean, even to me, even to me, it's just like that would be it'd be heartbreaking. It would be just hard to comprehend. You were around the black hole for what you felt like was a moment, and then everything around you, everything that you knew is gone.
Yep. So if theoretically you get to the speed of light, the universe would be gone because you would not age. Well, the universe ages infinitely in whatever time you went. You would actually get to the speed of light.
But everything that you knew, the
Got another
universe.
hour. 12:20.
Oh, it's only 11. You're right.
Okay.
And previously I mentioned about two theory. That's just one theory. The another theory is the expansion of the universe is faster than the speed of light. And so anything, any object at the rear of the universe, and will move faster than speed of light. That's a theory.
That you said we move faster than the speed of light?
No, I mean.
Or that there are things that move faster than the speed of light?
So the expansion of the universe is, I know where I found it is faster than the speed of light.
Yeah. All right. So.
And so everything at the rear of the universe will move faster than the speed of light.
That's. I've heard various things that not only is the universe expanding, but it's getting faster, and there's so much we don't know. I will circle back to that in a second. Recognize that this formula here tells us of the fact that we'll never get to the speed of light. That's what the math is indicating here, and there's a lot of evidence to support that. A couple of years ago, there was a group that came out with findings that they might have exceeded the speed of light. Now, as physicists, considering the amount of evidence supporting the fact that we can't get there, the fact that they did get there suddenly made them go, something's off here. And so the press got a hold of it and said, hey, faster than light travel, which the press should never have done. The physicists were going, we don't know what's wrong. We don't know why we got these results. And somebody later described what they had gone through is that probably the most thorough examination ever of trying to understand what happened. And I think it came down to a faulty circuit, that there was some bad data. So there are theoretical particles also that later on they looked at this and they said, well, you can't go the speed of light, but is there anything that says we can't go faster than the speed of light? Or if there's something that starts faster than the speed of light, they can't drop down below the speed of light. They will always be faster than the speed of light. And there's a theoretical particle called a tachyon, which in theory does that.
Isn't that something that goes backwards in time?
Well, and this I think will connect potentially to something Kong had said. If I shot you with a tachyon gun, from our point of view, if I shot you with a tachyon gun, you would be hit before I pulled the trigger. So, in a sense, there's a backwards in time aspect to it from our point of view. However, if such a thing exists, then we need to redefine time. And I think that gets back sort of what Kong was saying about, is the universe traveling faster than the speed of light? I think the way space is behaving is something that we don't understand. I'm still going to go with the party message that I don't think it is. But it's also possible we need to redefine time.
I'm just going to go with, I don't know, and I'm not sure I want to know.
Yeah, when they say space is expanding, my vision of this, and it could be that I've just gone down the wrong path and just refused to shake off of it, is that I sort of picture space as these individual cells. And what's happening is that the cells are expanding. So it looks like something is farther away, but it really is in some sense the same distance away. I mean, it's still moving, but it's not, we're not dealing with faster than light travel. We're just dealing with a change in distance, such as that's a meter right now, but that's a meter later on. And so from our point of view, it looks like it's traveling a farther distance, but it's really traveling the same distance. That's sort of my take on it, but I could be completely off base on that.
Yeah, I'm thinking, what if the universe what we call the universe is just a known universe? What if the universe is just is already infinitely large? It's just a huge void, and and everything that we see is, and there's more beyond what we can see with our current technology.
Well, I think we've pretty much accepted there is a lot more than beyond what we can see. However, the part of the way you described it as universe is this big void out there. Physicists basically have defined space as there has to be something there. If there's nothing there, it's not officially space. So radiation of some sort, there has to be something there. It can't be completely devoid of everything.
It's what I'm saying. Yeah, well, I guess what I'm trying to say is there could also be stuff that is beyond what we see, but beyond what we can see, but it's too far away for us to detect. Yeah. That's what I'm theorizing.
And there are other theories about there's multiple universes, and the universe is all, think of the universe as a bubble all expanding, and another one over here is expanding in something larger, and eventually those two will meet, and the universes will, suddenly there'll be a pocket between two universes.
Yeah, I've thought about stuff like that, the multiverse, where different physical systems altogether. They're thinking that I have this crazy idea that there are actually, that this multiverse is there's 5 dimensions. One of them is time. Then there's the 3 dimensions, and then there's the 4th dimension where one could move between these universes.
And there are theories out there. In order for string theory to work, it has to be, I think, 10-dimensional. But there's a lot of these that the theorists come up with that basically it's not unallowed, and so they write papers on it. And like many theorists, they come up with stuff and throw it against the wall, and at some point it'll stick. But most of it is just pure crap. But we don't know. There's so many things that theorists have come up with that we just can't test yet.
Yeah.
Or ever, I don't know. All right, let's take a small break there. There seems to be some restlessness here. Take a small break. We'll come back in 5 minutes or so and talk about the muon experiment and address, speed of the universe. That was mentioned earlier by Con. We'll talk about that in the Michelson-Morley experiment. Pretty sure that'll work.
It'll show 10 numbers on screen.
Yeah. All right. Let's take a look at satellites. Earth satellite. The altitude of a satellite, I just looked that up in the break, is 20,200 kilometers. Radius of the Earth is 6,400 kilometers. Yeah, I'm going to talk after that. What is the force that keeps the satellite going around the Earth?
Gravity.
So that force, using mg like you would for weight, doesn't really work here because the value for g is unknown to me when you're that far away. So g, mass of the satellite, mass of Earth, divided by r squared. That's the formula for the force due to gravity. That's the general formula. It's traveling in circular motion, so that's centripetal motion. And then if you happen to remember what the formula for centripetal acceleration is.
I don't. I'm just looking at trying to look that up.
So basically, we're going to plug in F equals n, and we'll get there in just a second. So the force is this generalized formula: mass of satellite, mass of Earth over r squared is equal to the mass of the satellite times centripetal acceleration. All right, so now we're ready for it. V squared over r. Okay. At least it seems familiar to some of you.
Yeah.
So this is the radius of the orbit, so I'm going to cancel out one r on both sides. I'm going to cancel out the mass of the satellite. So what I'm left with is that g times the mass of the Earth over r is about equal to the speed of the satellite squared. So we can figure out how fast the satellite's going. G is a constant-ish, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times the mass of the Earth, which is about 5.98 times 10 to the 24th kilograms, divided by the radius of my orbit, which is the combination of those two things, which is 2, 6, 6, 0, 0, and putting it into meters. So 26,600,000 meters, 600,000 meters. And that's the speed squared.
Over what? The nm squared over?
Newton meter squared over kilogram squared.
Oh,
If I round it, it's about,
You give me V or V squared.
oh, no, I'm giving you, V squared there.
Okay. Either one, it just, eventually we need to get to V.
Yeah, V, which I need to square root that. 3,872.332. Wait, 3. Sorry. Oh, you want to keep on going? Oh, yeah, that's why you're asking 3.
No, he's looking for units.
Oh, units. Meters per second.
Yeah. You could go through and do the dimensional analysis, but it comes out meters per second. All right, so it's going a little under 4,000 meters a second, which matches the government site controlling these things. Said it comes out to about 14,000 kilometers per hour, which comes out to pretty much that. All right, so obviously well below the speed of light. So let's just take a look at the effects of it. This is why I asked how many decimal places does your calculator go. 1 minus 3.8, I'm just going to round that off to 4,000. Just 4,000 over the speed of light, which is 3 times 10 to the 8th. So it's going to be bunch of zeros.
5 zeros to be exact.
It's 5 zeros?
Yes. And then 6, 6, 6, 7.
Missed
5
zero.
zeros.
Yeah, one more 0. There you go.
So that's a fraction.
Everyone else get that?
Yeah.
You got 2? All right.
I got 1.
Is your calculator on float or is it on?
Yeah, it's on float.
You got a different number?
It's 1.0 repeating.
All right, so you got a bunch more zeros.
My calculator round up to 1.
Oh, I didn't square it. That's what it is.
Oh,
Ah.
yeah. Yeah, I didn't either.
Yeah, so I just moved up to 1.
Comes out to 1. All right, so it's a tiny number.
Yeah.
So we'll have to approach it from a slightly different point of view. All right, so gamma is equal to 1 minus v squared over c squared to the negative 1/2. All right, that it's nothing particularly. I just rewrote that formula using negative exponents, which is 1 minus, what is just v squared over c squared?
Let's see.
3 times 10 to the 8.
Yeah, that's what I thought.
1.7 repeating times 10 to the negative 10.
10 to the negative 10?
Yes.
All right. So when you're dealing with really small values like that, there's an approximation technique. It's similar, actually, you can derive the small angle approximation using the technique we're about to do here. In calculus, did you get to the Maclaurin series or Taylor series? Does it sound familiar at all?
I think he mentioned Taylor series once, but we never discussed it.
No. Taylor series is a way of taking something like this, or taking a sine function, cosine function, and writing it as the sum of a whole bunch of just normal x raised to some power divided by some number.
Never mind.
Pardon?
Did you mention Fourier series?
It is similar to that as well. There's something known as binomial expansion in this particular case, and if I have 1 minus x to the nth power, where x is much less than 1, and I think that qualifies here, that this is approximately equal to 1 plus n times x. So this will end up being, wait. Make sure my sign is right here. Okay, 1 minus n times x. Yeah. And so again, if the other number is incredibly small compared to the first number. And so this becomes 1 minus negative 1/2 times that, or plus 1/2 times 1.7 repeating times 10 to the negative 10. So 1 point, whatever half of that is. So 7 repeating, that's 16 ninths, 8 ninths, so 1.6, 7, 8, 9.
It's 8 repeating. Well, to the negative, yeah, it's 10 to the negative 11, so 10 zeros and then 8 repeating.
All right. It's an incredibly tiny number. So generally, when you're dealing at 4,000 miles per hour, 4,000 meters per second, which is roughly somewhere between 8,000 and 9,000 miles an hour, relativistic effects generally are ignored. However, think about a day that passes on Earth. So one day that passes on Earth, or actually every 1.0 all that days on Earth, would be the equivalent of 1 day for the satellite. So they're out of sync, just a little bit. Well, let's think about how much that affects it. So it's traveling at, I rounded off to 4,000 meters per second. Times, well, so over the course of a day, we have this, that's how far they are off in terms of days, so let's put it in terms of seconds, so that's 8,600, 400 seconds per day. So if you multiply that times 86,400 seconds, how much time, what's the second difference between Earth and the satellite?
$86,400.00001.
86,400.00001.
One more zero. 4 zeros.
All right. Again, it's just a tiny little change of a second. But so the difference between how much the Earth ages and how much the satellite ages is basically that number of seconds. Well, if you're traveling 4,000 meters per second, that's time, so times 0.0001, lost a zero again, 0.01 seconds, which is the difference. 0.04.
It is 0.04.
So 0.04 meters, so 4 centimeters. In other words, if the satellite thinks it knows where it is, but it's suddenly, by its calculations, is now 4 centimeters off every day after a year, that's a whole bunch. So multiply times 365
14.6
meters.
meters.
That can make a huge difference if you're trying to put a missile down through a porthole of a ship, or if you're doing precision bombing, or if you're trying to make sure that you're driving along. 14 meters. How many times have you been driving on a road within 14 meters of a river? Or ditch, or industrial complex.
Or another car.
Or another car, definitely. So, which will probably have huge impacts for the driverless cars, or the, whatever they call it, the driverless cars.
Yeah.
Yeah. So, it's important that the satellites know where things are. Now, I guess potentially we could, track the position of the satellite every single time, but now
I feel
we
like
could probably do anyway. But
do you think the satellites would offset themselves because of that?
this general relativity, actually special relativity and general relativity are both taken into account in programming.
Okay.
So that is actually an application of special relativity that is felt by us. I was about to say seen by us, but we don't actually see it. It's done behind the scenes. So not a huge effect, but it accumulates over time.
So the time on different planets in our solar system is different, right?
All right, so if you were on those planets, the time would be different than on here.
Other
Yeah.
planets.
Yeah, because they're traveling at a different speed than we are.
Yes.
And people at the equator are traveling faster than people at the poles because of the spin of the Earth. And so people at the equator will not age as rapidly as the people at the pole, or the other way around. So let's get into the twin paradox.
Into the what?
Twin paradox.
That's not in the book, is it?
Oh. All right, since I have the biggest opening towards Thomas. Thomas, as I'm walking towards you, from your point of view, how fast am I going?
About a meter per second.
Okay. From my point of view, he was coming at me at a meter per second. He was right.
Yes.
Both right.
What's your say?
Yes.
Yes?
Yeah, yes, both are.
Both are right. Or they both wrong. All right. So how fast something is going depends upon point of view. Earth. Rocket ship. Rocket ship goes shooting off at 0.9 times the speed of light. Goes off to a distant planet X, and then returns. From the person on the rocket ship's point of view, 1 year passed. With beta equal to 0.9, that corresponds to 2.294 years passed on Earth. That's basically special relativity plugging straight into that formula right there. From the Earth's point of view, that was from the Earth's point of view, so that's Earth's point of view. The rocket went and came back. From the rocket's point of view, the rocket didn't go anywhere. The Earth went out and came back, and planet X over here came towards the rocket and went back. So, from the Earth's point of view, the Earth stayed still, and the rocket was traveling. So actually, from the Earth's point of view, we'll just say 1 year passed on Earth for 2.294 years in the rocket, but from the rocket's point of view, 1 year passed here, and 2.294 years passed on Earth. Which one was moving depends upon the point of view. So this is rocket's point of view. However, when they get back together, one of them is going to be older than the other. This is the twin paradox. The idea was that you have a set of twins, one twin is on Earth, the other twin is in the rocket. They are identical ages. The rocket goes out, comes back, or from the rocket's point of view, the Earth goes away and comes back. One of the twins is older, one of them is younger. So if point of view is all that matters, then we have a paradox here, because in the Earth's point of view, the rocket traveled and the Earth stayed still, so this was the proper frame. And from the rocket's point of view, the rocket stayed still and the Earth moved. Only one of these is correct, though. And so the big question is, what is the difference between these two scenarios, besides point of view? This is the correct answer. That, by the way, that the person on the rocket ages a year and the people on Earth are older. The twins are no longer, the twins are no longer the same age. Biologically, no longer the same age. So what is the big difference in the points of view?
One is moving at 0.9 times the speed of light.
Relative to Earth. Or down here, the Earth is traveling at 0.9 times the speed of light relative to the rocket.
Oh. Yes. I'm not sure.
Imagine that you were on Earth during this or in the rocket. Would you feel the same thing?
No.
What would be different?
It would have felt like I would have been gone for a year if I was on the rocket, but if I wasn't on the rocket would have been gone for 2.294 years, and then it comes back.
Okay, but that doesn't explain how it feels. What would you feel differently if you were on the rocket? Assume the rocket's spacious enough and you're not claustrophobic. And you don't hear the engines.
I
When
would
you
have
have gravity.
What do you mean?
Like, if you're in a rocket, most of our, well, we don't have it, some sort of artificial gravity, so you wouldn't.
Oh, so you're picturing it sort of floating around?
Yeah.
I actually never pictured that. I always picture sort of a Star Trek kind of ship.
Yeah. Or like, what is that movie, Mars, where their spaceship actually spins, which causes, I guess, artificial gravity.
Yeah, let's assume there's artificial gravity. That's not the issue.
Yeah. That's just a thought. I feel like it's different.
There's a fundamental difference between the rocket experience